All right, let's get started. So welcome everyone. Today we're going to be talking about reliability in a connected world. We're going to be integrating Ansys Mechanical and Sherlock. My name is Kelly Morgan, and I'm a principal application engineer at Ansys, and I've been with Ansys almost 7 years now. And Gil?
My name is Gil. I came to Ansys through the acquisition of DFR Solutions, which created Sherlock, and I have been since January of 2013. So I don't know what that means. I think, is that 7 years?
About 7 years, yeah.
Almost 8.
Great. And today we're going to be really covering kind of how Ansys Solutions work in terms of electronics reliability. So we'll talk briefly about, the role of Ansys Sherlock, Ansys Mechanical, and really today we're going to talk a bit about, how electronics are really a multi-scale problem, inherently multiphysics, and our goal really is to develop really a true digital twin or virtual replica of our electronic systems. And along the way today, we're going to be talking a bit about PCB modeling, substrate modeling, using a variety of techniques that Ansys has introduced over the years, both for traditional circuit boards and also for things like flexible PCBs. And we'll chat a bit about that today. And we'll also talk a bit about techniques that really span or really bridge the gap between very small scale features, things like die level, package level sort of assessments and larger sort of kind of system level sort of studies. And this will be submodeling, really exciting topic we'll talk about near the end of the presentation. So this is where I usually start when I talk about electronics reliability. And really when we think about it, I mentioned right away multiphysics is really a big aspect of electronics. And you can see here that really we start off looking at it. Inherently, electronics are, of course, an electrical problem. We look at things like power and signal integrity throughout the design process and design cycle. And Ansys has tools that help you address things like EMI, EMC concerns, et cetera. Tools like Ansys SI Wave and HFSS help with that. But when we think of a electrical device in operation, we think of joule heating effects that arise. And we think of that inherently leading to a need to look at the thermal behavior and your cooling strategies. And really Ansys IcePack and our thermal solutions really help you with that. So right away, we look at electronic systems, we're looking at electrical and thermal behaviors. And then what this often does is this feeds into more of a mechanical viewpoint. As things are in operation, they're heating up, we want to know not only what is the maximum temperature maybe throughout the board, but we want to know if I go through a number of thermal cycles, what's that going to do to my solder, my board? Is it going to cause a premature failure? What happens if I include or account for things like shock and vibration? What's that going to do to my system? And then really, as we start to account for the various physics, the final goal oftentimes is to understand what is my predicted life? How long is my product going to last? Is it going to last for 5 years, 7 years, or less? And what sort of changes do I need to make sure that I meet my product promise effectively? So what we're going to start off today is talking a bit about different modeling techniques. And of course, in terms of electronics, you can imagine, again, the disparity of scale we tend to look at. And if we take a look here right away, we often start off at a very small scale, chip and die level, all the way up to even the server room level. And, Gil and I talk regularly about, these sort of things. And Gil, what are your thoughts in terms of modeling things in terms of such a small scale all the way up? What's your approach when you tend to look at these sort of things?
So thank you. So this is actually what we mean by multi-scale multiphysics simulation. So you can see that the scale here goes all the way from the nano, which is on the die, right? We think of dies in terms of nanometers, submicron, definitely submicron geometry. And that starts with the GDS2 layers and all the way IC packages all the way out to, the board, the system, the whole level. And there's all kinds of things that get added. But the reality is that the cooling starts at the server level. So the heat comes from the chip, the cooling comes from the server. So we really kind of need to go all the way from the chip to the server room and then back to the chip in order to find out what's really going on. And there's all kinds of physics that happens. We have CTE mismatches. We have mechanical vibration. We have insertion forces onto connectors. We have boards interacting with one another. So we have boards that might be hot like a power board next to a digital board, and if you put it in exactly the same boards in a different configuration on the server, they might actually have a different temperature profile. So all of these things work together. So that's why you have to do like a multi-scale analysis. And when you model the die, it is inherently different than modeling the chip. So the die has different problems, like actual physics that happens inside of it. They have different problems. And people who model, or actually people who are trying to design IC packages, have different problems than people who are trying to design PCBs. So each one of them has a slightly different approach to simulation, but they all need to talk to one another. And that's where kind of the Sherlock and Ansys family work together. Kelly, you're muted.
Muted. So you mentioned something quite interesting there, and that's, different users, different customers of Ansys will tend to operate in different spaces. You have somebody who focuses more on IC packaging, others are working more at the board or assembly level, and a lot of the thing we need to consider is data exchange. We need a means of transferring data kind of up the chain effectively, taking package information and looking at it in a board level, and then looking again, going backwards, thinking of kind of a system aware sort of behavior or process for looking at IC packages and chip die level assessments in detail. So across the board, very interesting in terms of what can be done. So, and how do we achieve this? Really one of the questions is, and as we look at, again, the disparity of scale that we tend to look at, one place we start is usually PCB modeling. It's a very classic piece we'll look at. And again, it often depends on the features of interest. As Gil mentioned, we're looking at problems that maybe the board is really on a millimeter scale, but then a lot of the other very fine features, if you're looking at traces and vias, are obviously on a much smaller level, much smaller scale, and we need to be able to handle that. And so overall, between when we're looking at Ansys Sherlock and Ansys Mechanical, we have the ability to look at different ways of modeling PCBs, and a lot of times, in addition, packaged substrates. And these sort of techniques range from very simple, looking at a board, let's say, as homogenized, where we kind of have lumped properties, smeared properties between copper and dielectric material, all the way up through, let's say, we have maybe smearing, but for each layer. So at each stage, as we go from left to right, we're looking at kind of an increase of fidelity, whether it be, again, very, very coarse, very quick method, all the way up as we go to the right-hand side. Now, as we'll get into more in a few minutes, we've introduced a couple of new approaches the last few years. One is called trace mapping. We'll get more into this in a little bit. It's effectively a mapping of metal fractions from an ECAD file directly in, and imagine mapping those sort of metal fractions onto an existing mesh. So we get a very good idea of what the resolution looks like in terms of copper content throughout a board. And as we need to consider more detail, especially for those fine sort of features, we can start to use the so-called reinforcement approach and trace modeling approaches. So we'll take a look at these in a little bit more detail and talk about where and when we want to use them in a minute or two. So Gil, what are your thoughts in terms of component modeling? There's a lot of ways we can do it. It can either, again, much like boards, be fairly simple or more complex. Where and when would you, from a component level, want to include leads and solder in detail? Where would you want to maybe think of it as just a simple component mounted on a board?
Excellent. So here's the thing that I think of. I look at three things. I look at the failure mode that I'm trying to model. I look at the damage indicator, and I look at the area of interest. So if I have a failure mode that is a board level failure mode, so it's the connection between the component and the PCB, I don't necessarily always need the internal component details. If I have something that is happening, that is the failure mode is happening away from where the heatsink is or wherever the potting is, then I don't necessarily need to model the potting in that specific location on the PCB. Now, same thing for traces and vias and all of that. So if you think in terms of, and this goes back to like first principles of how we do simulation. If you think of the failure mode, when you look at the area of interest and the physics of what happens to it, then it pretty much, it creates the need for you. If you want to do things for a BGA for, what's the difference between one ball to another, you need to model both balls. If you're just looking at a BGA as a one big, mass that sits on a board and the effect that it has on a board, you don't really need to worry about that. If you're looking for vias under a BGA, and different via structures and how they affect the BGA solder ball, that's exactly when you need to model vias under that BGA. So it really, the question is, it depends. And then the three things that I look at is failure mode, area of interest, and the governing physics of it.
No, absolutely, I agree, and I think it depends again on what your scope is, what your focus is, and that may change. Early on, you may be trying to understand kind of global behaviors, global characteristics, and as you start to need a little more refinement, we have a lot of techniques, again, both in Sherlock and mechanical, that allow you to really zoom in and hone in on what you're looking to do. Now, another key part here is when you're looking at electronic systems, there's often a really a lot of complexity, and the complexity arises from just the sheer amount of geometries that we have, right? Geometric features. If we're looking at not only the number of mounted, kind of surface mounted components, but we're also looking, again, traces, vias, let alone if you have a housing that you're also including. So there's a lot of complexity geometrically. There's also a lot of complexity in terms of material behavior. Some components tend to be more linear elastic, but a lot of times there may be parts or components that like solder behave more like a viscoplastic solid. So there's a lot of different things we need to account for. And then, as we mentioned, there's a lot of kind of physics conditions that we need to account for. Things like for drop test or kind of thermal cycling, even static loading. But but to kind of go back to what's going on in terms of a geometric complexity, part of historically one of the challenges has been how do we even get or acquire material properties for all these parts. We had to have to go back to data sheets. We'd have to maybe take a look at whatever information we have in house, go to test. And that's really where Sherlock comes in. So Gil, in terms of what Sherlock has to offer in terms of libraries, what really advantages do customers see in going to Sherlock to build up models in this way?
There's no secret. There's no genie. There's no AI behind any of this. This is just a very, very smart Excel sheet. That's what Sherlock does. It does exactly the same thing that you would do if you had this task. So if someone gave you a list of 200-300 components or 2,000-3,000 components and said, hey, I need to find all the information, you would go to online, you would find the part number, and you would start populating data. The thing is, we have people, they are librarians, all they do is populate this data. And they do this for you. It's part of the license of Sherlock, right? So you can give them a list of parts, and then they create those part entries for you. That includes their material properties, that includes their leads, that includes guesses about die size, because look, a lot of these things, you would have to 3D section it or some kind of X-ray to be able to find out what's inside of it. Our librarians are really good guessers because this is pretty much what they do all the time. They're pretty much experts at this thing. And that's the advantage that you get. You get somebody to create this library for you. We do this for materials. We do this for solders. We do this for components for different packages as well. And the idea here is not to do something that you wouldn't have done anyways. We're just speeding up the process for you. Instead of you having to do it, all you have to do is check someone else's work. You just have to look and make sure that our librarians did a good job for you.
Yeah, I mean, if you were to do all of this yourself, I mean, just the sheer number of components, the level of detail, it would be normally a time-consuming process. This, and I think we're on the order of hundreds of thousands of parts now in terms of the library, and it's growing all the time. Kind of.
If you had to do this yourself, Kelly, you just wouldn't do it. Most engineers would just say like, whatever, I'm not doing all of this. I'm doing like the 5 interesting components on the board, and I'm just not doing the rest of them. But with Sherlock, because it's so available, it's so there, you pretty much just say like, why not do it?
That's absolutely right. And actually, one other point, you mentioned cross-sectioning. Just so everyone knows, we do actually have a reliability engineering services team too, that came as a part of the DFR Solutions acquisition. So we actually have team members that work on consulting projects. We have a lab facility, so we do a lot of physical testing, teardowns, and many other things too. So we actually have other services besides just what we have to offer in terms of software. So it's a very exciting sort of time really at Ansys in that respect. So in terms of the different techniques we had mentioned, we really want to focus on three kind of main approaches. And again, we often want to think about what sort of level of detail do we need at a particular point for a particular application. And one of the first ones that comes into play, and this has actually been kind of developed, I would say, in two different avenues. One was Ansys prior to the DFR Solutions acquisition had been developing a trace mapping approach, and so had really the Sherlock software. So there's actually a couple of techniques you can use, but in general, the process is very similar. Trace mapping, basically, we start with an ECAD file. So you can imagine taking an ECAD file you would export from your favorite EDA tool. There are many of them out there. And usually we end up with, ODB++ file, could be a Gerber files, things like that. And again, the challenge here is if we were to account for all the traces and all the vias in full 3D fidelity, again, the sheer number of components gets to be really high, as is all the connections between them. You can imagine all the contacts trying to mesh. Gets to be very challenging. And we'll get to when and where you want to do that here in a little bit. But the trace mapping approach basically takes the layout and basically understands from that what is the metal map all the way through the board and in plane, so full 3D, basically what is the metal fraction at every point. At that stage, we can actually go ahead and map using our so-called trace mapping process, map that to a mesh. And the great thing about the mesh at this point is that it starts with a very simple geometry, which you again import from the ECAD file. And you have effectively a stack up of plates, basically one for each layer. And the great thing is now that I can do this, I can actually map the metal fraction onto the mesh. And what we'll see is when we do that, we have an accounting for every element what the metal fraction is, which means that I can go in and Ansys will automatically tell me, well, maybe if I have 80% copper and 20% dielectric in a certain area, it's going to go ahead and kind of prorate and kind of adjust the properties to account for that metal fraction. So what we get is instead of doing a simple smeared sort of approach, which, obviously going back in time had been used very heavily, this is where we can get a pretty accurate accounting of where the significant amount of copper or metal is going to be located in the board. And this gives us a very kind of quite a bit more accuracy without a lot of additional expense necessarily, because we already need a mesh and we're already going to be defining material properties. It's just now we're doing it more locally effectively. So this is a very, very popular technique that comes into play. Gil, you have any other thoughts on this approach and how customers have used this either in mechanical or Sherlock in the past?
Yeah. So this approach is really good to find differences between east versus west of the board. So you can see areas that have higher metal fraction, east versus west. Combined power and digital boards have this all the time. And then the other thing that you can do in this one is this is really good for thermal conduction simulation. Anyone who's doing thermal conduction through a board, you don't really need individual traces to be there. You just kind of need to know what is the conductivity in that area of the board. And this is really, really good for that part. I've seen that the layered approach, so just the regular layered approach, is kind of the same for top versus bottom of the board. So like anything to do with board bending. If you have these boards that have east versus west, then you can't do that. But most boards have like an even spread across the place. You can also use this if you do the mesh fine enough. And again, with Sherlock, you have something called modeling regions, and you can select one region and have a really, really tight mesh in that area. So let's say underneath the corner of a BGA, you want to actually model in a like sub-millimeter, like 0.1 millimeter mesh. And then everywhere else, you want to do like a 1 millimeter mesh. So it's like a 10 to 1. And then what you get is you actually get the traces in the vias under the BGA corner, and then everywhere else you just kind of get like good enough properties. And you can do this with a combination of what we talked about with the, we're going to show in a second with the, so yes, there are specific applications, anything to do with thermal conduction, anything to do with basic CTE, this works.
What other approaches are possible? And early on, we talked about, kind of the smearing and homogenization. We just talked about the trace mapping approach. So this is actually the reinforcement element workflow, which is something we've introduced fairly recently, kind of takes things to another level. And so in general, if we kind of take a step back and look at reinforcements generally in engineering design, and reinforcements are really all around us. You think of, I mean, classically things like reinforced concrete, right? We have rebars embedded in a matrix, basically. You can imagine, again, kind of composites, traditional kind of carbon fiber epoxy composites. We have individual strands, again, embedded in a matrix of material. Same thing from biomedical applications and many others. So this is, these sort of structures come up again and again. And again, how do we actually model these? Again, trace mapping, as we saw, is one such approach. But Ansys, under the hood, actually has a technology that are really meant for these sort of cases. We call them reinforcement elements. They've been available actually for quite a long time in APDL, effectively the Ansys parametric design language, which is kind of under the hood of Ansys Mechanical. What's really been improved though over the years is the ability to have a first of all, the graphics enablement, being able to now more readily develop such models graphically has improved. But also the level of meshing required has also been improved a bit too. We can actually have these sort of so-called traces. In this case, we would have surfaces representing traces, surfaces or beams, basically, basically modeling vias. And instead of treating them as separate shell bodies or beam bodies, we're actually a matrix of base elements. And these are your traditional, typically solid elements many times for that. And what's great about that is I can actually have a moderately coarse mesh. I don't have to have an overly refined mesh to account for that. So what we're trying to do is really kind of have a nice kind of balance between accuracy and expense. So a little bit, a bit more accurate than trace mapping, but not as expensive as trace modeling, which we'll get to in a minute, and we usually reserve for very special cases. Further, this sort of reinforcement can be thought of as discrete, so individual fibers, like in more on concrete, but it can also be more smeared or homogeneous, basically, and that gets us more to where we would use this in a electronics context. And so what we've introduced really is a workflow that spans, and I really love this because it really spans really a lot of our class-leading tools. So looking at Sherlock to help generate the models themselves, and we'll mention that more specifically in a minute. But actually generating the traces there, and then making any geometric modifications we'd like in Ansys SpaceClaim, sending it over to mechanical, and then also then simulating and post-processing. And you can start to again look at an entire PCB, but then still again get an understanding of what's going on very locally in the trace regions. And so in a second here, we'll kind of go through more step by step. And so really the first step here in this workflow is to start with Ansys Sherlock. Sherlock, as we've explained, really has a lot of key strengths, including being able to import various ECAD files. And Gil, in terms of trace, generally working with traces in Sherlock, do you have any comments on kind of how that's done and the efficiency in doing so?
I would say Sherlock is kind of like easy peasy lemon squeezy. The fun part about working with Sherlock with traces is that Sherlock does not care about where you get the information from. You can have one layer coming in from an ODB++, another one coming from IPC 2581. You can take a picture and bring it in. So Sherlock is really agnostic about where the information is coming from, and it basically washes the information together and can export it in any format you want. You want it into APDL, right-click export to APDL. You want it into Workbench, you bring it into Workbench. You just want a step file, take it as a step file. You can even mesh it in Sherlock using the regular Ansys mesher. It sends it to the regular Ansys mesher and just export a basically geometry nodes material properties in the form of a CDB. So Sherlock kind of takes anything and export anything. We like to say that we are agnostic about the import and export of information. You can even bring in drill holes using an Excel sheet, just XY locations and like drill diameters. You can bring them in directly from an Excel sheet, even if it's not embedded into your specific ECAD file. And the fun thing is you can change things on the fly. You don't like this trace, you can change it without actually having to open any other ECAD tool. And you can do all of that in Sherlock. And then when it comes out, it still comes out. It looks exactly the same. It looks like a step file, or it looks like a SpaceClaim file with trace reinforcement. And with the same right click, you can convert a reinforcement into a full 3D solid model. And that's, again, gives you the ability to do that multi-scale thing. And we can do this for a board. We can do this for a BGA. We can do this for on-die metallurgy. So like GDS2 layers, no problem. MCM files, no problem. ODB++ or any kind of Gerbers, no problems. And even onto the larger scale, all of this can propagate.
Yeah, and in terms of this particular, what we're looking at right now, you can imagine taking this sort of image basically, and you can kind of go in one of a couple directions. One would be what we'll be continuing to discuss now, the reinforcements. Imagine each of these being sent out as basically maybe a surface body for resolution. And as Gil mentioned, you can actually within Sherlock actually continue to build on this and start to build full 3D trace models. So there's a lot of, again, you can start with a lot of the same place. There's a lot of commonality to these workflows where we start with an ECAD file, and then it's kind of up to as to what direction you want to go. So this is really a good starting point, is being able to read and understand what's going on with the traces. But Sherlock will also, again, given the component libraries, given everything else we've discussed, can help you build what I would say is the balance of the board. So build up the rest of the PCB, the stack up of layers effectively, and then also the components that we have, again, assigned with appropriate material properties, geometries, to your required level of fidelity, whether you want to include solder, whether you want to include leads or not, that's up to you. But really, that's the key thing. And really, the export, as Gil mentioned, is fairly straightforward. You right-click, and you can export either this level of model, or you can export for the various layers the reinforcement information. Now, what happens is, we can then go to, if we wish, go to Ansys SpaceClaim. And this is not always required. Sometimes we'll need to go in or want to go in and make some changes, suppress some pieces. Maybe eventually you want to add a housing. And so you can certainly do that. And then what we do is we go over to Ansys Mechanical. And there's been a number of enhancements recently, first and foremost, being able to bring in, of course, these surfaces and assign them not as a shell necessarily, as we normally would treat a surface in a 3D problem, but we can assign it as now a reinforcement. So Ansys knows that it's going to be treated as a reinforcement element rather than a shell, as I mentioned. We can also specify thickness, and we can also specify whether it's a discrete reinforcement, smeared, or homogeneous sort of reinforcement. And really at this point, it's the rest of the mechanical analysis is much like any other analysis. We set up our loads and boundary conditions, we run, and we, basically get our results. And that's the final piece. And again, if you're looking at it, this is a thermal result, and you can imagine looking again, kind of big picture, kind of at a more macro level, what's going on maybe in an overall package. But then as you kind of drill down, given that we have reinforcements enabled, we can start to see what's happening very locally. And you can see even to the point where we're looking at some of these very small sort of copper features in this case to try to determine, again, kind of, in this case, it's a temperature variation, but it's also true for various structural responses as well. And so, Gil, what are your thoughts in terms of where and when you would want to use the reinforcement approach?
So I go back to failure mode, area of interest, and the damage indicator. A lot of times, anything to do with very specific trace heating. So this is a very big deal for our customers. If you have a component that's getting hot and it's heat sinking through the board down to the other side. So remember, the structural part here might not be the biggest deal for me, but the thermal is really important. I'm literally using the board as my heat conduit, and I'm putting a lot of vias under that component specifically to create a heat sink to the other side of the board. That the trace reinforcement is basically the killer app for that. There's no better way. It's faster and easier and simpler, and it just looks cool. I mean, the picture that you get at the end, you can actually see the efficacy of the individual vias and how good they are, because you can change plating thickness. You can actually work with it in a way that is kind of hard to do if you're just doing regular trace mapping, and kind of expensive computationally to do if you're trying to do a full 3D trace model. So that's a really good one. The other side of it is anytime that you're trying to model, there's a specific thing called hot tear that happens can happen to BGAs during reflow, especially secondary reflow when you do the other side of the board. And there's basically no other way to do it other than with reinforcement or with full 3D trace modeling. In full 3D trace modeling, you can maybe do it for 4 or 5 traces vias around the corner of the die. But with trace modeling, you can trace reinforcement. You can basically do it throughout the entire package. You can take the entire package, do a trace reinforcement for it, and actually see what's going on. And you can predict if there's going to be a hot tear just by looking at the stresses in the solder interconnects. It's great.
Yeah, so this also then kind of leads you to the next thought. Well, if I have maybe a trace mapping, maybe I'm using reinforcements, what about those cases where I do need to account for kind of full 3D fidelity? And I'll get to that in a second. But first, I should mention that we've also done some physical testing and looked at kind of the results and compared the results from reinforcements with physical test, and they've compared very favorably. In this case, we're taking a look at kind of distortions in the central figure here from Ansys Mechanical, and then comparing that to what we're finding from a digital image correlation, basically physical test. We're finding that we are capturing a lot of the the sort of features that we expect. So a lot of these approaches have been validated through internal testing, through our own labs, or through various customers have also done a lot of kind of comparisons, and these various techniques are very appropriate for these. Now, I should mention, and I'll mention an asset we actually have on hand that we can share with you. One thing that comes up is, well, what if in one case I may be able to trace map the entire board. Maybe in another case I'm using all reinforcements everywhere. What about hybrid modeling? Now that we have a whole roster of techniques, you can also think about, well, what if I actually have a kind of a trace model, full 3D model on the top layer, and then maybe in the interior, imagine having that be maybe reinforcement elements or trace mapping to try to, again, get that extra bit of fidelity where and when I need it, and then everywhere else we have a kind of a middle level of fidelity maybe, but we still capture, again, the best of accuracy and expense. So that's one thing I definitely challenge everyone to think about is, hey, how can we mix and match to come up with a very efficient model?
And I think the way, like Josh and Tyler, who are and Michael, who are our modelers who use Sherlock to do all these kind of fancy things, they actually make the kind of pictures that you see here all the time. Yeah. They have this thing that they do where they have a mapped trace mapping in the middle of the board, and then the top and bottom layers are full trace modeling, and like full 3D trace modeling. And what they get is they get basically the outside of the board behaves like traces, and the inside of the board behaves like bulk. And again, this is like more of a hybrid modeling. This is more of a hybrid approach. It's a little bit harder to do. And then we've seen that they're getting very good results. And not only that, the customers really, really like it. People really like seeing, man, you really do see the effect of the individual traces, and then you can capture the overall effect of the board as well, which is great. I mean, that's exactly what we're looking for in terms of improvements to the way that we used to do electronics.
Yeah, and if you're looking at, even especially if you're mounting, package, and we have solder modeled, it's nice to be able to model and actually connect the solder, the solid geometry to maybe, to the board, again, not through maybe an area that's just been smeared, but we actually have a, proper 3D geometry, or we have something nearby with the reinforcements where we capture, especially right at the point where we need that detail, we have the 3D kind of getting away from that critical joint. Then you start transitioning, much like you would transition a mesh in general, right? You'd have a fine mesh maybe near the solder and transition away. We're not only transitioning the mesh away, but also our strategy changes as we go away too. So I think that's really the forefront, is being able to kind of mix and match a lot of these approaches. And what this leads to is the final piece, which is really trace modeling. And we've alluded to it a few times, but this is actually kind of what it sounds like, is really a full 3D model of critical features, right? We're looking at in this case, we're looking at traces, we're looking at vias, we're looking at pad stacks, everything we're pretending to look at. Gil, in terms of your, again, kind of leading back to what we've been talking about, where and when would you like to see, or when do you use this approach?
So a lot of our customers are starting to use stacked vias. So not just regular plated through holes, but they're using either filled vias, like buried, or even plated like through vias that are filled, or they're doing stacked versus staggered. So the whole question of stacked versus staggered, there's no question that staggered is better. You sacrifice real estate to get better reliability. We know how to model this. We've been modeling this for years. It's just become more apparent. More people are starting to use this kind of stuff in high reliability applications, which are difficult, and they're looking for yields. So anytime you have those, this is excellent. Another thing that you can do is you can actually use the Sherlock trace models in other physics applications. You can actually do crosstalk between traces across an entire board, and not just like two little traces that sit one next to each other like in HFSS. We're talking about like long traces or whole nets that work across an entire board or across an entire substrate. So anytime that you want, and anytime you want a pretty picture, look at that thing. Pretty much sells itself, right?
Absolutely. And again, if we think back even to the hybrid sort of approach, again, imagine having, even if it's not the full, full 3D, full board, imagine having this locally critical areas and then transitioning to the other techniques we mentioned is often a very kind of useful approach. Now, we talked about, kind of PCB modeling, I would say in general, but really one of the other things we're looking at Ansys is how are we addressing emerging technologies? And, I've been trying to look at efforts for, how do we model adhesives effectively? There's a lot of kind of science and simulation aspects that we need to look at. How do we account for things like ingress of water and dust? Another one that's very popular is not only, looking at, circuit boards themselves, what about flexes, flexible PCBs? And we've come up with, I would say, a couple of things. One is certainly core technologies, but also appropriate workflows that really handle this. And you and I've been chatting about this recently and looking at kind of the lower right-hand figure here. Maybe you can kind of tell everyone kind of the approach that we would take for actually modeling this sort of flex PCB and what sort of the benefits would be to that.
Yeah, so this Flex PCB, which by the way, this workflow is available to anyone who wants it. It's an open source workflow. There are two failure modes that people are looking for. Number one, they want to bend the flex as much as possible, which is a problem because the flex does not want to bend. They want to bend it around a battery. They want to blend it around, whatever inside of the case, because real estate is expensive. The other thing is the connection between the flex portion to the rigid portion is kind of a harsh connection. So they want to know how much mitigation they need. Usually there's some kind of an epoxy bead at the connection. So they want to know the effectiveness of the epoxy bead, different materials, different bend radii. That's really kind of the thing that people are looking for. The approach in Sherlock is you basically model it as a regular PCB with trace modeling in the middle, and then you can connect them together in mechanical and run all of the analyses that you want, the bending analyses that you want. And because Sherlock creates the traces as is, you can actually bend them. What I think is really cool about this is that, first of all, this workflow is enabled by the fact that connecting different PCBs in Sherlock is very, very easy. So different portions of a PCB, splitting up PCBs, doing all of that is very, very easy. The other part is that the trace modeling, because it's so effective and because it's so easy to do, it actually gives you the ability to look at, and this is a relatively simple flex connection, but if you have traces on the flex, plus if you have components sitting like soldered directly to the flex, which we do see that once in a while, this gives you the ability to do that. And one of the main things is if you have split flex, so it goes from one board to many boards, you have kinks in the flex, and that causes a really, really high stress region in that location. All of this enabled by, Ansys Sherlock goes into Ansys Mechanical.
Yeah, and there's two cases that I tend to see. One is actually modeling, let's say, the forming process, actually modeling and taking what you've done in Sherlock, taking a mechanical and actually physically bend it to see what the response looks like. And that'll give you a good sense of kind of the pre-stress condition once it's kind of installed. The other thing we've been working on in combination with RBF Morph is the ability to take and we've talked a bit about trace mapping. This is true of not only for trace mapping, but for other approaches that we've talked about. But basically taking a mesh with the trace mapping, and actually normally we start off with a flat board, but now we can actually morph the mesh. So instead of modeling the actual process of the simulation, if we know its final state, map the mesh from its original position to the final position. And we see that here. We see it's flat and then it kind of goes maybe to a wavy position or kind of wrapped in a 180 sort of sense, and basically have the mesh kind of go along with that, including, as we see here, a lot of the features, things like the trace mapping that we would see. If we were using trace modeling, we would be mapping, again, the nodes and elements that would be representing those sort of features. So this is helpful if you just want to know maybe post-installation, maybe you just want to know what happens maybe after that point, right? So there's a lot of different technologies you can use, again, depending on the scope of what you tend to be looking at. And so kind of one of the final things we'll look at here is, again, we've been talking a lot about, the fact that there are very fine features, very small scale features, all the way up to very large scale features. And how do we really, address that sort of disparity? And really the technique we use quite often is called submodeling. And sometimes we'll call it global local modeling. You'll see that described in the literature. The idea is really the following. The idea is we'll start with a global model. Now, again, if we're looking at a kind of a board like this, with solder, with underfill, die, everything on it, you can imagine the mesh count getting pretty big pretty quick. And again, the more number of nodes and elements we have, the longer it takes to run. So what we often do to be efficient is run a global model with maybe a middle level of fidelity, something that's a bit, moderately coarse or middle level fidelity, so I can run it, fairly quickly. Because a lot of times, especially if we're doing thermal cycling, we could also be looking at maybe a nonlinear analysis. And so what we'll do is we'll model it in that sort of sense. But then from a global analysis, we usually kind of pick based on max stress or plastic work or whatever our metric is, we'll usually pick maybe the critical feature. In this case, maybe a critical solder ball. And the idea is, and again, what you see in the schematic on the upper right-hand side is system B here. On the left-hand side is our global analysis. But then what we'll do is basically carve out in a separate sort of geometry, we may carve out that critical feature. In this case, you can see I have the stack right above maybe the critical solder. At this stage, Ansys can automatically basically map all the displacements from the global model onto wherever I've extracted this local feature right here. And then I can refine it to whatever degree I'd like. I can make it a very refined mesh and then run independently just that segment. So it's a way for us to really zoom in and really capture additional fidelity, locally, rather than trying to do that on the entire board, which is very, very expensive. And in fact, we can do this in multiple layers if you really wanted to. I could start with a global board level model, go to a model that we see right here, and even zoom in further if we need to effectively. So we use this a lot in general in structural mechanics. We use it a lot for welded joints. In this case, we have solder joints are usually a big candidate for this. And you can kind of see at the very end the level and the accuracy. We see the sort of detailed solder responses. At the final stage, by the way, we could actually even start with a trace mapping maybe in the global model and then go to a full 3D trace model in this feature. But by the time you get to this stage, it's actually really a great spot to use that sort of modeling. So Gil, I know you've used this quite a bit over the years, and you've also used kind of a companion approach, sometimes we call plug modeling. What's your take on this approach?
So first of all, it used to be really difficult to do this submodeling. Ansys's workbench has made it incredibly simple, where now I'm going to say this. Anytime you're doing bump level simulation, this is the best known method as far as I'm concerned right now. It is better than doing the plug approach because the global model takes so long to solve, because there's just so many degrees of freedom there, especially since we're getting to bump counts that are in the thousands, like tens of thousands. It just becomes, we have to do so much simplification in the global model already that adding that extra, you might have 500,000 elements just in the local model. It's just, this is the best known method for it as far as I'm concerned. The other thing that I really like about submodeling nowadays, and I use them interchangeably on a little bit, insert versus submodel. There's some things you just can't do at it depends on what you're going to do with the model in general. There are just some things you cannot do with the submodel. If you want to change a geometry, if you want to change a global material, you kind of have to run the global model again. What's really nice, though, if you're just looking at different geometries, let's say different ball geometries, and it's kind of the same diameter, but maybe the pad opening is a little bit different. You want to look at slightly different UBMs, slightly different thicknesses of the polyimide layers in bump passivation. Those things, you basically run the global model once, and then you can run 5 iterations on the submodel, and it's a lot faster and easier, and it gives you a completely valid model. The plug model, I think if you still are using the kind of global local plug model approach for maybe the board level, it's okay. At some point when you get to do really multi-scale, when you're looking at 1 micron features versus millimeter features, submodeling just makes more sense. But I use them interchangeably. I don't actually, I'm not actually married to one of them. It depends on what's working, and also it depends on the sophistication of the user. Some users don't like to use they want to do a conformal mesh on everything, and then you have to use a submodel because you can't get. It's practically impossible to get a conformal mesh on something where you have a plug. It's very difficult. You have to use contact elements. So it depends.
Yeah, and actually, so as a kind of adjacent to this, we're working on some really interesting things in Ansys Ellisdyna right now. So this is kind of usually like a one-way sort of approach. We think of a global informing what's going on in a local model. We're actually working on an approach in Ellisdyna that's kind of a co-simulation, if you will. So imagine having a global model, maybe with a simpler representation like a beam, and then passing that to a local sort of model, and then accounting for very fine level details, including things like fracture and other behaviors, and then passing that information back to the global model. So, we're definitely at the forefront of looking at new strategies, new approaches in this sort of, regime here. So to kind of summarize here, there's a lot of techniques that we learned about appropriate for, again, fine scale modeling, macro level modeling for PCBs, packaged substrates, across the board really. So where do we want to learn? Where can we learn more? So really a couple of key places. First one is the Ansys Learning Hub. So we have a lot of references, a lot of resources, training materials, lecture notes, videos. We have a room just for electronics reliability. So we've been populating it with content related to Sherlock, related to mechanical, also adjacencies, things like adhesives modeling and working with other things in kind of related industries and related applications. So definitely if you have access to Learning Hub, great place to learn. Secondly, we also have some additional workshops and other resources. So on the learning room for electronics reliability, I've posted a workshop that walks through end-to-end the trace mapping workflow, including how to use the resulting model in a random vibration analysis, modal and random vibration, kind of thermomechanical. Excuse me. So walks through end-to-end exactly how to do that. So you learn a lot from that. In terms of some of the other approaches we mentioned, we actually have some on-demand sort of video content that's available. We have content hosted on the DFR Solutions, the Ansys Electronics Reliability sort of website for the reinforcement element workflow. And if you have access to Sherlock, you can start right away, use the installed tutorial board, and go end-to-end from ECAD file all the way through a completed model. And it takes around maybe 20, 25 minutes if you watch the video. And then the other one, we've talked a bit about hybrid modeling. We actually have a webinar that one of our colleagues, Dr. Nathan Blateau, presented a little while back that walks through, the hybrid modeling approach, which really, of course, encompasses the different techniques we mentioned today. So with that, thank you very much for listening. And Gil, do you have any other final comments from your side?
Yeah, when it comes to workflows, we also, all of our ACE team, so Kelly's kind of alluded to it, all of our ACE team will create custom workflows and help you with scripting and create workflows for your specific problems. We have a bunch of these for electronics reliability that are kind of, it's too many of them to really go over right now. But if you have something and you think it's special, I promise you, we've probably done it before. So just let us know and we'll give you that workflow. And thank you very much, Kelly. This was excellent.
Yeah, thank you, Gil. Hopefully everybody enjoyed the session and enjoy the rest of the event. Thank you.